This is about a subject that not very many people talk about. Hang on a second. Sorry about that. We talk about a subject that engineers don't really get taught in schools. They talk about, they teach us all about building processes, but they don't teach us much about how to program them. And this is about how some programming tactics that we've learned by burning our fingers and by trading ideas and by, basically it's a bag of tricks. So sit back and think about some of these tricks. Oh, and by the way, if you're working on the security side of this thing, well, when you get into the PLC, everybody just kind of says, here there be dragons. And that's an example of what's the edge of the map, which is what many cartographers used to do. Let's review real quick some of the 4 languages and how they should be used. There are 4 primary languages. The obvious one that we need is ladder diagrams, but the one that everything is supposed to compile into is instruction list on the bottom. That's something that we've been using a lot. You've been seeing a lot in some of the attack code. The advantage is it's supposed to be most portable. The others are like structured text. That's good for if you've got high-level math, any major calculations. That works real well. Ladder diagram and function block diagram, well, there's a religious argument depending on which side of the Atlantic you're on. The Europeans prefer the function block diagram, the Americans prefer the ladder diagram. It actually has to do with who does the programming. If you have electricians that are moving into the programming area, you'll want ladder diagram. If you have programmers, they'll look at function block diagrams and they'll think, yeah, this looks better. When you take all these little sub-programs and put them together, you get the sequential function charts, and those are what you use for handling state changes. That's for like transitions between different modes. It's a very handy thing to use, and that is used regardless of which one of the 4 primary languages you're using. A lot of the vendors will tell you, oh, this controller is huge. You can put everything in the whole plant into one controller. Don't do that. Really don't do that, because now you're just one fuse away from total shutdown. Don't do that. It's not a good idea. You like to keep the program segments small. You want to be able to distribute the processing among lots of little processors. Put the processors as close to the I/O as you possibly can. Now you're probably wondering, this is a security conference. Why am I talking about this? Because you've got to get good diagnostics out of these things. All the problems that people encounter are, gee, that looks funny. Well, what is it? Well, it's probably an instrument problem because they've seen lots of instrument problems. So there we have it. You got to keep the controller close to the I/O. There's less to go wrong that way. Put networks out there. The peer-to-peer networks, please don't run them into a big switch. Consider the possibility of just using a crossover cable between them, because that gets you out of a problem. If somebody attacks the switch or if the switch is misconfigured, that gets you out of that problem. So it builds a resilient thing to do. Let's move on. The typical PLC scan cycle looks like this. You have your physical input scan here, where you take your inputs. You have your logic computation. You have your housekeeping for keeping track of all the things that go on inside the PLC, like keeping track of counters, keeping track of timers and other timeouts and things like that. Then when you're done with all that, you go to your physical output flush. That's where you push most of your output. Now, mind you, this is not specific to any particular brand of PLC. This is what they all do. And then, ladies and gentlemen, this is the network service part here. I want you to note how little time the PLC actually spends talking to anything else. It's not its primary purpose to talk to the rest of the world. Now, if you have a multiple processor PLC with its own dedicated network processor, okay, that's a different animal. But the primary processor is not here to service all the rest of the network. So if you have these ideas of, I'll just use the PLC and talk to the rest of the world with it, please don't do that. Now, inside here, we're going to talk about, this is the subject of most of the talk here. First of all, check for system faults. Read and validate your inputs. You want to make sure as you go down up this list that you want to be able to do things like indirection boundaries. And I'll get into that in a second. First of all, you want to tell your HMI to read and write in between designated array structures. Why would you do that? Well, if you've got a protocol-sensitive firewall, it makes your job a hell of a lot easier to configure. And you don't have to go sorting through many, many different things in the protocol structure. You also have you have an opportunity to validate everything. Everything that comes into the HMI, you send it in through one big block. The HMI can then look at it and say, does this make sense? And likewise, when you send any commands out to the PLC can validate what you've got. So here's how it would keep an attacker at bay. Now, mind you, this is what you do if you don't get the PLC you asked for. Sometimes you really would like to work with, say, I'll mention a product by name that I have used and actually like. I have no real relationship with them, Bedrock PLCs. They've actually put some thought into this. There are other vendors out there as well. One of the things that you can do is you have your buffer, the buffer for the output from the device. It goes, oh, didn't mean to do that. You have your buffer here from the output of the PLC. It's a read-only buffer. In other words, it's for the read-only from the perspective of the HMI. The problem is the PLC writes to this thing. Now let's say something comes in and writes to that read-only buffer from the HMI. Let's say another device, a rogue device comes in the network, sees that buffer and tries to write to it. What happens? It's going to go through that entire cycle again. It's going to rewrite it right over it. You've basically overwritten anything an attacker would write. And oh, by the way, you could probably go sensing for that, and then you could say, hey, somebody's trying to write to something they shouldn't. So you can actually detect something. It's not perfect, it's not ideal, and sometimes it might not even be an attack, but it's something you could look for. The other thing you have to do is validate your inputs and outputs. So, for example, there's a lot of PLCs that will let you write directly to a counter or a timer. Don't do that. If you've got a counter, or better yet, if you've got a timer, do you want to put a value of 655 seconds into something that's only supposed to be 1.35 seconds long? Okay, you probably shouldn't. If you've got some kind of a timeout that says your valve should close within 1.35 seconds, or timeout, you don't want a 10-minute timer on there. So validate it. Nobody does. Everybody just says, well, the HMI won't do this to me. Why not? It might not even be the HMI on your network. Don't trust it. Other things you want to do, modern PLC cycle times are fast. You might want to look at possibly debouncing inputs. A lot of I/O cards give you that opportunity, but if the I/O card doesn't do it, you can do it within the PLC. You go looking at things that are related, like forward and reverse. If you've got forward and reverse asserted together, well, obviously, you got to raise an alarm. Somebody's doing something wrong, and it might be your own logic, or it might be a piece of wiring in the field that's gone awry. Maybe something got wet. You don't know. Same thing with start and stop and open and close, all of these other things that you can do. You have your PLC application code points for the you have alarm points for the HMI to say, hey, I've got a code anomaly of some kind. You really want to add those in. Nobody does. It's not in anybody's specifications. That's why it's not there, but it's something that you need to add in. You also want to look at variable frequency drives. This is a bad case of, please don't do this. If you don't have a burning need to talk to all the different 200-some parameters that are inside a variable frequency drive, please don't put a hose, a network hose, going into the variable frequency drive, because what that does is it exposes all the guts and all the alarm points and everything else about the variable frequency drive to the PLC. You might have a reason for doing it, but if you don't, if you can just give it a plain old 4 to 20 milliamp current loop, think about it, because that limits the attack surface. So, next thing we're going to talk about are motors and actuators being restarted too frequently. This was very similar to the Aurora attack. We'll have more to talk about that in a second. This is the motor restart delay diagram that I showed you. That thing there is not ordinary PLC code. Ladies and gentlemen, that is a physical timer. I want that physical timer in the field. This belongs in the motor bucket. This is an oversimplified diagram of what you will see in the motor bucket. You'll notice that over here the start motor has to go through the start permissive. The start permissive is here. That's the motor running. If the motor's not running and this timer hasn't timed out, don't let it restart. Why would you do that? Well, let's say you've got a water pump pushing an awful lot of water up a hill. Okay, that's a thing that you do not want to restart right away, especially with a line start motor. If you do, you could very easily snap the coupling bolts on the shaft. Very bad day for a lot of people. Don't go there. Put this circuit in, it'll save you a lot of grief. I want to emphasize that if something tries to restart the motor during that timeout period, you need to investigate that. It's really something that has to be done. In terms of diagnostics, keep a couple of things in mind. In North America, we have 60 hertz AC. In Europe, it's 50. That cycle takes 16 milliseconds or 20 milliseconds in Europe. If your cycle time in the PLC takes longer than that, you need to break the PLC code up, and you probably want to go find out what's using up all your time. You may also want to look at the control voltage coming out of the motor bucket, because if the control voltage goes away, it means a lot of other things can't work, and a lot of the indications you get will be garbage. So it's a good idea to keep a look at the control voltage to make sure it's there. You might also, just as a curiosity, look at the current on that control voltage as well. Same thing with the 4 to 20 milliamp current loops. You've got a 24 volt supply that you've got stuck somewhere. You might want to look at all the current coming out of that, because what you get is you look at the other devices in the system, and you should be able to add up the currents, and they should all agree. And if they don't, investigate. You might have one side of it grounded. You might be close to blowing a fuse. There's all kinds of possibilities. And then, of course, latch transient events at the PLC. Don't do it in the HMI. The HMI doesn't talk to the PLC very much, and as you saw earlier from that diagram, it doesn't always get the most up-to-date information from the PLC. Get it from the source. If it matters to you, have the device latch these things for you. Here comes another fun thing. A lot of times, we tell the newbies, don't do indirect addressing. In other words, don't look for the value of one register in another register. Now, there are reasons for doing this. Sometimes you need a lookup table. Sometimes you need to do sequencing and staging. There are reasons why you might need it. I'm not going to tell you don't use it, but if you are, consider putting it in an array with a binary size, and I'll show you why. You'll also want the addresses to be checked before reading or writing to them. Let's show you this. Okay, this is your array. The example here is the array is 8 members long. This value here is a poison. This value here is a poison. In other words, if you get to them, that's your fence post error. That's what generates your, hey, something's wrong with the code minute. These are your legitimate values. So what you do is you take your indirect address, you add your offset, and you run an AND on it. And that way, by running an AND, you have mathematically eliminated all the other possibilities. You're never going outside that array. You're doing the check in the code. That's for self-preservation. You also want to talk to peer-to-peer devices. That does not absolve you from needing to validate your inputs. You need to validate your inputs. Always validate your inputs. There's also a practice that was used years ago that said OPCDA is great. Let's use it to connect two incompatible PLCs through the HMI. Again, please don't do that. Okay, that was back when protocols didn't actually exist to do peer-to-peer properly. There were no standardized protocols. Well, that's not true anymore. Ethernet IP has been around for a long time. We don't need to make the HMI a critical asset. That's not a good place to be. You should also have a heartbeat going back and forth. And if it fails to get the heartbeat, you know the link is down. It doesn't matter why. If the media itself is down, you don't care. It's not something you really want to. It's your ultimate debug. My logic here is not talking to that logic there, so I can do plan B. That's what it means. There's also internal status registers. This is another thing. Ladies and gentlemen, all the PLC vendors, just about all of them, have gone through a lot of effort to build diagnostics into the PLC. How many messages were received over a period? How many were sent? What's your cycle time? Have you hit have you done a divide by 0? What other kinds of things are going on? There's a whole bunch of diagnostics that are built into the PLC. Most people ignore them. I'm telling you, you should really do that. You should check those things. One of the interesting things you can do with communication statistics is you can, if you know the time down to the millisecond, and let's say you're working on a master in a SCADA system. Okay, so the SCADA system knows when it's sending things over a given 5-minute period. The PLC knows when it's receiving things over a 5-minute period. You count up the number of messages received from the master. It should match what the master thinks it sent. That way you know if anything else is getting in there. It's a crude method, but it's another layer of security you can add in. Also, if the PLC has a hashing function to detect its code version, please use it. Tell the world what version of code you have installed in that PLC. Here's another one. This is just a diagnostics purpose. Avoid sets and resets. You're familiar with not using goto in most languages, and sets and resets are kind of like that in the PLC world. There are edge conditions that are different for everybody. I'm going to recommend that unless you have a burning need to use them, and sometimes you do, you really shouldn't use them. You must also check the sets and resets to make sure that they're not being asserted together, because that's an undefined condition in most PLCs. Every manufacturer will do different things. It might be the last thing in the ladder that gets asserted, or it might be the first thing in the ladder, or it might alternate like a flip-flop. You don't know what it's going to do. And you don't know what the edge conditions are, and God help you if you happen to have a set and a reset and an actual coil on the same address. That's a real no-no. I don't know what the hell will happen then. So you really have to do a cross-check across your code. That's what the cross-reference is for. Use it. Use it. And group it together. Don't put them in different parts of your ladder if you're going to do that. My God, that's a recipe for disaster, because then you think, oh, wait a minute, did I delete that thing, or what happened? I don't know. So at the end of the day, if you do this, it'll make your diagnostics a lot easier. Anyways, those are tips and tricks that my mentors taught me, that I learned the hard way by burning my own fingers, and that other people have relayed to me. Are there any questions?
Hold on.
Yeah.
Jake, we have something for you.
Welcome to Beer Isaac. and
Isaac! Yay!
Because you're a part of the DNP3 technical committee, it's a special number. Take a look.
Wait a minute. 5-4. Oh my God. Oh, 5-4. That's the beginning of the preamble, the DNP3 TL3 frame.
So sorry to say that the 06 was already taken.
Ah. Yes, thank you. Anyway, back to the PLCs. Any other comments, thoughts?
Hey, Jake. What about like testing and validation of PLCs? Are vendors providing anything in the way of ways to unit test or do testing of logic with hardware in the loop before you deploy something in the field, or is this more like punch card programming where you spend hours and hours laboriously thinking about it and then hope it just runs correctly?
This is a headache that goes beyond the manufacturer, because a lot of times what the PLC does is it responds to I/O that you get, and sometimes the I/O itself hasn't been fully thought out. Sometimes you get chattering pins, sometimes you get hunting movements that really screw up your code. So you can write pretty good code on a simulator, and a lot of vendors will provide you with a simulator, and it works, but you're not really giving it a real-world test. And I remember having to code an awful lot of garbage into a PLC because I had a valve position. I was sending a position to a valve, and it would hunt back and forth across that position before it settled. And that was because it was using an analog controller that was not properly adjusted. And we didn't know how to adjust it properly because we couldn't get support from the valve actuator vendor. They wanted to upgrade the unit because it was over 5 years old and had been sitting on the construction site for all that time. So these kinds of things happen. So when you say, can we validate the code? Well, the code isn't always the problem. It's the I/O. And you get to that I/O and you make lots of tests. That's another thing you can do, is you should make the PLC able to divorce the logic from the I/O so that you can do I/O testing. So you can see exactly what it does when you do it. And use a graphing function within the PLC sometimes. It's gathering the data at a fairly high resolution, so you can actually see what's going on. And it's best to do things at the lowest level possible. Always push these functions as close to the field as you can. And do as much peer-to-peer communications. That way, if anything fails in the middle of it, you can, at least if it fails at the higher levels are what tend to get attacked more because that's what people understand. At the lower levels, you find fewer and fewer people that actually understand what goes on down there. That's changing a little bit these days, obviously, when we see PLCs playing tic-tac-toe, but, you know, it's still an issue. We should really be pushing things closer to the field.
How much frequent it is to get training like this to people that program PLCs?
You know, that's a really sad subject because a lot of vendors are very happy to show you all the wonderful features your PLC has, but they're not very good at showing you, well, good programming practice. And it's not like we learn it in school. You know, I studied binary Carnot mapping and things like that. And I didn't learn tactics like this. I learned them on the job. And I don't know of anybody that actually teaches this. This is one of those things where I just burnt my fingers and I decided, you know, I've got enough information here, maybe I can put it into a presentation.
Is the market now ready for services that automatically vet the code and tell you if there are instances of these cases, and are you aware of any?
I've been through other people's code on PLCs, and sometimes I've learned from it, and sometimes it was a learning example of what not to do. Yeah, it goes both ways. Sometimes, like, if you look at old PLC code, sometimes you'll actually see people reuse coil and register values. And
Just copy and paste, is that what you mean?
no, it wasn't copy and paste. It was in a day when memory was short, and you couldn't get a whole lot of memory for PLCs, so people would, in different modes of the program, reuse various registers.
Within the same program, okay.
Don't do that. But you'll find old code that often does. And it was a tactic back when memory was expensive.
I see. So you're not aware of any company who is offering a product to scan the code and tell you, hey, there's a problem here?
I'm not aware of any. I haven't, maybe there are people out there doing it. It would be different for every major vendor. The 1131 standard that's out there has done a lot to standardize these PLC coding schemes, and a lot of good has come from it, but at the end of the day, it still goes into different models of processors in the field. So it's really hard to write a standardized piece of code that would review PLC programs.
Right. All right, thanks.
First off, good presentation. Second, can you talk to everyone about why you should do this as a methodology as part of like your FAT, your SAT, and just general system security engineering? You know, it's not being taught, but you're educating people now, so it's no longer, you know, something that people aren't aware of. So how do you start pushing this as a methodology where people do these checks as just part of normal design integration? You know,
That's a difficult thing to do. Contractually, the problem with control systems engineering is it occurs as one of the last elements of a large capital project. And it's unusual to not see things at that stage of the program that are over budget and over budget, beyond, or late. So basically, you're coming in, and it's a very high pressure environment, and we get what we call a drive-by integration, where somebody drops an address on a device, gets it up and running, does the minimum amount of things required to get it working, and they run away. And I have that problem in a lot of places because the PLC code delivered by integrators, for example, is, well, it meets the contract. It does exactly what it's supposed to, but it's not well written. And there's nothing I can do about things like that except review the code that they wrote and try and improve upon it. Well, that takes time. So larger organizations can get away with actually hiring a separate control systems integration staff and doing that in-house. That doesn't scale down very far. You need at least, you should have at least 5 or 6 engineers to do that properly. And if you don't have that many, then you're kind of up a creek. You have to rely on the integrators. The integrators themselves, well, unless they see a market for aftermarket services, like, for example, security review, they won't do anything either. So there's a gap in there, and we have to think about how we're going to deal with that gap.
All right, well, thank you so much.
Thank you for having me.